we will proceed with the interferometry. Before we proceed, one more example, okay, just for you to get an idea. Of course, first, how to couple light from a laser source or from a optical source. Okay, how to couple light from an optical source, maybe it's a laser. Okay, at present I assume that still you do not have much knowledge about laser. Okay, that's what I'm assuming. So but we'll just write a laser to an optical fiber. Okay, this one question. And what, right? So what will be the beam divergence angle right, from the output end of the fiber of an optical fiber. Okay, can you imagine? See, if it is an optical fiber, what we have learned, there are different types of optical fibers, right? Single mode, right, optical fiber, wherein only one wavelength mode gets coupled. Means we can couple multiple different wavelengths. However, finally, while transmitting, only one mode will get transmitted effectively, while other modes will get leaked out the core clade region, which is a single mode fiber. If it is a multi-mode fiber, it will allow transmission of different modes. Okay, transmission of different modes, etc. And graded index fiber, which is right, which allows less of interdispersion. Now our question is, how will we couple the optical, right, light from the optical source? In order to couple the light from the optical source to the fiber, as the fiber core diameter is very small, right, we should be able to focus the light within that region, isn't it? Otherwise it cannot be coupled. Secondly, the acceptance angle plays an important role. If the coupling light, right, the convergence, right, when we focus, it's going to converge, right, is angle is larger than the numerical aperture or the acceptance angle of the fiber, it will not be able to couple. What I mean is, let's say this is a focusing lens or a biconvex lens or a focusing lens. Okay, so this is a focusing optics. Okay, it's in focusing optics. Light is coming, okay, and it gets, say, focused, right, and this is coupled the fiber. Okay, and it is a core through which light gets transmitted, correct? So this is core, this is clade, and first thing is this beam spot over here, from the focusing optics point of view, the beam spot over here on the fiber should be comparable, right, to the core diameter. Okay, first thing. So the beam spot size should be comparable, right? Focusing, right, beam spot size should be comparable to the core diameter of the fiber, right? That's correct, or core radius of the fiber. Okay, one point. Second point is, let's say we know optical fiber with a core and a clade has acceptance angle, right? So this is what light is coupled, getting coupled, while the acceptance angle of the fiber is this. Okay, this is based on the numerical aperture of the fiber in this right angle, and this is the acceptance angle. Okay, the optical fiber has acceptance angle which is decided based on the numerical aperture of the fiber. Numerical aperture of the fiber, this is decided based on the core refractive index, clade refractive index, correct? Core, clade, right, etc. Now and the this angle, right, where the optical beam source is getting coupled with the fiber, is decided based on its own, right, beam characteristics. The lens what we use, as well as the beam size before focusing and the beam size after focusing, they will decide this right angle. And if this angle is more than the acceptance angle, right, of the fiber, then we end up with a difficulty in terms of loss which is being experienced by the light when it is getting transmitted through the fiber. Why? Because some part of the light which is more than this acceptance angle will get lost while it is traveling through this fiber and through the clade region. Okay, and finally the output, right, light will be intensity will be smaller than, right, what it is getting coupled over here. Okay, are you clear about this? Now when the light is transmitted out from the fiber, right, when it is when the light is being transmitted through the optical fiber, and at the output end of the optical fiber, how this divergence angle of this light will be. So it depends upon two things. Maybe first and foremost, here I must tell you that what I am talking about here in this case also optical fiber, is the case of a multimode fiber. Okay, multimode fiber. Okay, multimode fiber. In case of, so in case of a multimode fiber, the output, at the output end, the beam divergence will also be dependent on the beam divergence of the light, right, optical light which is coming out will depend upon the numerical aperture of the fiber. Okay, so the numerical aperture decides the divergence of the beam which is coming out. Okay, so the divergence angle of the light which is right at the output end will match with the numerical aperture. Is it okay? Is it? It looks right. It's okay, right? However, in case of a single mode fiber, so this is again a case of a multi-mode fiber. In case of a single mode fiber, the coupling part, okay, the at input end, the coupling end, so this is a core, this is a clade. The core diameter is such that it is matching with the right single mode, right, transmission through this optical fiber, and the core diameter is quite smaller. Over and above, it will the coupling will depend upon is decided based on the Gaussian beam, right, characteristics. Okay, Gaussian beam characteristics. So when we talk about laser optical sources in terms of laser, etc., we will discuss about this Gaussian beam characteristics. However, in case of this single mode fiber, when a laser light is coupled the fiber or a light, first of all, in the focusing on, it will follow a Gaussian beam characteristics and independent of the numerical aperture of the fiber. Okay, it's basically Gaussian. In case of a laser, if it is a laser only, we will be able to observe a Gaussian, right, beam characteristics clearly, and this beam waist over here, beam waist of this laser beam at the focal position should match with the core diameter of the fiber, okay, and since it follows a Gaussian beam characteristics, so we will see at a later stage that the Gaussian beam characteristic has a different divergence angle, okay, much smaller than the conventional, right, optical beam sources, optical light sources. And here numerical aperture doesn't come into picture, rather it's only the beam waist matching with the core diameter, the light will get coupled, okay, and at the this is the input end, right, at the input end, okay, and at the output end, the beam which is getting right transmitted at the output end, the light beam will again follow beam characteristics matching with the Gaussian beam, okay. The divergence is decided based on the Gaussian beam characteristics, not by the numerical aperture of the fiber, right. In case of a multimode fiber, the divergence angle is decided based on the numerical aperture of the fiber. In case of a single mode fiber, and if we are using a laser beam as an optical source, we will see that at the output end the laser beam will diverge. Of course it will, right, diverge. However, it is a Gaussian beam characteristics which will determine the divergence angle, okay, not the numerical aperture of the fiber. Numerical aperture of the fiber may allow larger divergence angle, okay, based on the numerical aperture over here, okay. However, this angle, right, divergence angle is decided based on the Gaussian beam characteristics, okay, characteristics. Okay. Secondly, when we are coupling light between two fibers, let's say we are, it's a multimode fiber, and when we couple light between two fibers, what will happen? Let's say over here we couple beam, then from here the laser the light optical beam is coming out, it is diverging, and then it gets, part of that will get coupled with the optical fiber, isn't it? So the numerical aperture or the divergence over here will determine how much amount of light is getting coupled with the fiber. If both these fibers are of the similar characteristics, okay, both these fibers have the same core diameter, same, as well as numerical aperture being the same. Okay, both are similar characteristics. So what we will see that the light over here, let's say the core diameter is let's say a, or core radius is a. Okay, core diameter. Okay, I want to. Sorry, I will. I'm sorry. I will. Okay, core radius is a. Okay, is a. So, and over here, when I will observe the beam size over here, optical beam size, it may be slightly larger, isn't it? Because of the divergence, and the divergence over here, this determines the beam size over here, isn't it? And this distance between, gap between them. If the gap is, of course the gap will not be so large as it has been shown over here. Okay, it is just to give you an idea. It may be of the order of few tenths of micrometer, or maybe, right. We try to bring two fibers as near as possible. However, due to some mechanical constraints, there may be a gap between two fibers of the order of few micrometers or few tenths of micrometers. So this gap, right, this gap will determine, and the numerical aperture will determine the beam size over here, isn't it? That means the beam size over here, if this is the core diameter, core radius is a over here, so this will be, this size will be over here, it will be a plus x, where x is equal to L gap 10 theta, isn't it? Approximately, correct? It is a very small size. Yes. Okay, so automatically you know now, right, in terms of intensity, right, the amount of light which is coupling to this, and right from here to here, there will be a loss in terms of intensity, isn't it? Because the core can accept only the beam size matching with the core radius of a, while the beam size over here, beam size over here is a plus x, correct? The beam size over here is a plus x, right? That means there will be a coupling loss. Okay, coupling loss. Okay, and coupling loss can also be determined by our approach of in terms of decibel, right? The coupling loss, right, in terms of decibel can also be determined by this formula. Is it okay? Because intensity of the beam will depend upon area, right, or power, which is getting coupled with, will depend upon the total area of this, right, which is getting coupled. So we expect it to be a, but the beam size increases, and hence the loss comes into picture. Okay, so this also you should understand. Now these are all simple things, simple terms, but when you are using it for various applications as in device form, these things will, right, inputs should also be useful, coupled with the optical fiber. Okay, now we go to the one more topic of importance, that is interferometry. So quickly, first I will explain you about interferometry in terms of free space optics. Okay, free space optics. Then we will couple it in terms of fiber-based interferometry approaches. Now, in case of a free space optics, there are various ways wherein this interferometers they work. One is Michelson interferometer. Okay. The second is Mach-Gender. Okay. Saginaw interferometer. Fabry-Pérot. Okay, these are all scientists. They have various configurations which are which were described by different scientists are named with their interferometers are named with their names. So Michelson interferometer, Mach-Gender, Saginaw, Fabry-Pérot, etc. Now Michelson interferometer. First of all, the interferometer is useful in order to determine one aspect. Okay, there are various other applications of interferometer, but in order to determine the phase change, or path difference, which is again it's indirectly a phase change between two light beams of with the same wavelength and polarization state, and when they are traveling, and if I want to determine the phase change between them, we can determine using interferometry approaches. So in case of a Michelson interferometer, the light source, okay, so let's see, so there is a light source, okay, and so output beam from this light travels and gets splitted into two arms. Okay, so this is beam splitter. Okay, and let's assume it's a 50-50 beam splitter. What it means, 50% of the light is reflected up like this, and 50% of the light is getting transmitted. Okay, so and over here, this is, let's say, mirror 1. Okay, here there's a mirror 2. So what do you expect over here when the light is getting reflected from here, and when there is a mirror normal to this beam, we expect the light beam to reflect back, reflect back. So maybe I'll draw the reflection with green line, so that so light will get reflected back over here. So what will happen over here, again some 50% will get reflected back here, and 50% will get transmitted, isn't it? Similarly, the light reflecting back from this mirror will also follow the similar, get transmitted, get reflected back over here. See, the input light beam is the one source, gets divided into two arms, and again this two light beams from this one single source, when they again travels back from this mirror 1 and 2, they again meet over here, let's say. And if we use a detector over here, oh my god, oh, that's very bad. Now, if we use a detector, right, what will we observe over here in terms of the overall intensity? It's the question, right? So what we are doing is dividing the light into two arms and then again coupling them over here, reflected beams, right? So what we expect at the output detector end, if these two arm lengths, okay, if these two arm lengths, let's say L1 and let's say this is L2, beam splitter to the mirror, okay, it is, if these two arm lengths are equal, right, then the light traveling in this arm L1 and the light traveling in this arm L2 will be traveling, if they are traveling equal distance, when they return over here, they will remain in the same phase as it was before the beam split, okay, and so they will be in the same phase. So in terms of electrical field, right, amplitude, they will add up, isn't it? Because both the waves have the same phase, they will add up. And in case if this arm lengths are not equal, still both the electrical field, right, will add up, but depending upon their phase difference, the addition will have different value, isn't it? And that phase difference indirectly, if it is let's say it's such that it is 180 degree out of phase, right, it will end up with output as 0 in terms of amplitude, right, electrical field amplitude at this detector point. So the intensity will be 0, isn't it? So so basically what we are trying to do is total, this may not be readable, so we'll take some other, right? So let's say total this, let's say electrical field is a combination of two components, right? One is E1, let's say E1, and the other one is, let's say, E2 along the arm length E1 and along the arm length, that is E2, right, amplitude wise, if we are trying to talk, okay. So if we try to, so this is, let's say, E0 cosine of let's say K1Z minus omega t plus E0 intensity, sorry, amplitude over here, when we are using 50-50, both are going to be the same. That's why I have taken in terms of same amplitude for both of these waves, except that both one wave is traveling little different distance, right? Sorry, KZ1, the other one is traveling KZ2, right, minus omega t. K is the propagation constant, right? Omega is angular velocity, t in terms of time, Z represents distance, travels. Okay, so this will be the case, isn't it? So, and as we know, right, as we know, this is, I'm talking in terms of amplitude, right, amplitude part. They will add up or subtract, etc. In terms of intensity, we know I is proportional to right, some factor, okay, maybe some factor is here, and it is E square, right, proportional to this. So total intensity is basically, I can say some constant, some factor will be there, E1 plus E2 square, right, even E2 square. So when I do this, half E1 square plus E2 square plus 2 E1 E2, right, can be represented. And we know a component E1 is nothing but E0 cosine kz1 minus omega t, E2 cosine kz2 minus omega t. So you will see that over here that component will appear. Okay, so half E2 square plus 2 what will happen, E0 square cosine z1 minus, oh sorry, z1, right, will, okay, it will be like this. Okay. If you simplify, you will be able to do mathematically, right, it will be this. And we know that I1 is proportional to half E1 square, I2 is half E2 square, correct? This also we know. So instead of E1 square, E2 square, I0 is half, and if you can write, then I0 is nothing but half of I1, sorry, I1 is half of I0 and I2 is half of I0. Both are equal, no, 50-50 magnitude. So, or we can represent this instead of E0 square over here, right? I can also represent it by I1 plus I2 plus 2 I1 I2 raised to half, right? It will be the equal. Okay. Cosine kz1 kz2 like this. So and that's okay, no? And further it will introduce one more factor, half. Somewhere it will become 1/4. Why? Because again part of the 50% of the light is getting transmitted. What we are measuring over here is half of that one which is reflecting. Please remember, although I have not included here, but that factor will come, half factor. Okay. Now what you can see here is when Z1 and Z2 are equal, right, we will add, it will add up overall, it will add up. Okay, I1 and I2 are equal, so what will be the outcome? I1 plus I2 plus I1 and I2 are equal, so into 2I, so 4I. Of course some factor will come here, so it will not be more than the I value, but what I am trying, overall intensity, I total, okay, I total, which is detected at the detector end, will be some, right, some constant into this factor, okay, this part. And if the Z1 and Z2 are such that this goes out of phase, 180 degree out of phase. This will be minus, right? -1. So this will end up with a 0 as the output, isn't it? Are you understanding? Yes? Is it okay? You will be able to, right, do mathematically you can derive. So if I see from the previous this case from here, if I see as this path length, okay, which is nothing but the difference between Z1 and Z2, and this is the intensity measured at the detector end, okay, detector end. Changes when Z1 and Z2 are equal, we will see maximum intensity, and when it is right, and when it is out of phase, what it means, when both these waves are when this path length becomes the difference in path length becomes lambda by 4. Correct. That means the difference in path length is lambda by 4. Correct. So what will happen? Difference in path length lambda by 4. No. So L1 minus L2. Okay. 2 times it is traveling, isn't it? 2 times L1. This Z1 is 2 times L1 minus 2 times L2, isn't it? 2 times it is traveling. So when the path difference is L1 minus L2, correct. I should write it in terms of, if I write it in terms of, I changed it to this, no, I'm so sorry. Instead of Z1, I write it in terms of L1 and L2. Okay, so double the right distances, so lambda by 4, then it will go to 0. Once again, as it increases, then again it will decrease, depending upon the path length it changes. Am I clear? The detector over here will detect maximum over here intensity, then it will go to 0 because L1 minus L2 equal to lambda by 4. That means this mirror, let's say, has moved by lambda by 4. So path difference in total, okay, becomes 2 times L1 minus L2, isn't it? Light will travel 2 times. So lambda by 4 L1 minus L2 will result into lambda by 2 right phase difference, so which will be equal to 0 over here. Intensity, it is out of phase, then again maximum, then again 0. It will keep repeating. Okay, of course there is a limit to this signal what we observe, assuming that it is a monochromatic light source. That means only one wavelength and only one frequency, right? This will repeat for infinite, right? Length path difference. Okay, so this is the configuration of Michelson interferometer. Okay, I will give you exercise in the sense that if you can, before we meet next lecture, if you can just try to go through the textbooks related to Mach Gender interferometer and Sagnac interferometer. Okay, next class of course I will try to explain, but I will go a little fast. Okay, if you can see through, I hope that you understood this right aspect very clearly. We do not know how will we make use of this in biophotonics. We are just trying to learn some important aspects, basics related to photonics aspect. We will try to couple it with the biophotonics, okay, at a later stage. Thank you very much.